Good morning, everyone. How's everybody doing today? Thanks for coming out in the rain. It was a deceptively hard rain as I was walking in. I started to come in without my umbrella and quickly turned back around. So, I am Steve Siceloff. I am Boeing's communicator here in Houston. I work International Space Station and Starliner's Houston operations, which means flight ops and crew training. And I also work Boeing's lunar exploration. So thank you for coming out this morning. The first time I was here at Space Center Houston was in 2000. I was a Cub space reporter back in Florida, and I had come out to see some of the first International Space Station crew before they went into space. And one of my first stops was here at Space Center Houston. You didn't have the 747 outside, but it was really cool, and it was one of those things that sticks with you. And y'all have great artifacts here. And one of the things that I wanted to make sure to tell y'all was that really the difference in all these museums, and I love museums and I love space flight museums and things like that, but you go to some of the museums in other places and there's not the people. You know, there's not the people not only who know what they're talking about, but who are excited about what they're doing. My recent example is when I was out at White Sands for the pad abort test, and great artifacts, some of the first V-2 rockets, you know, that they ever launched and things like that, but not really a lot of people. In fact, there were none. And walking through a museum with great artifacts but no people is a very different experience. So walking through Space Center Houston with y'all out there telling the stories, you're so energetic, you know what you're talking about, makes a big difference. And I think that's something that appeals to everybody. It appeals to the public and to folks like me who are, know that this is a great industry to work with. Everybody's excited to be in it. And so wanted to thank you for that. And that also brings me to the point of today, which is to thank you for coming to learn about Starliner. Starliner is Boeing's commercial crew spacecraft, and we're going to be launching on December 20th. So that is not this Friday, but next Friday. It's not going to carry a crew, but it will have some payloads on board. Mainly, it's a dress rehearsal for the crewed flight, which will come up early next year. We're going to fly it up to the International Space Station, dock. It's going to fly itself the whole way. Dock, and then undock and come back, land in New Mexico. So we're going to go through a lot of the details of that flight profile. So if everybody's ready, we'll get started. This is Boeing's spaceflight portfolio. International Space Station, which we're going to talk about in more detail later. Satellites, there's a lot of them up there, of course, and we built some of them. They do communications, we have commercial satellites, a lot of government resource satellites, exciting field. Can't always say as much as we'd like to about it, but that's the rules. X-37B also falls into that category of things we would like to say a lot about, but aren't really allowed to. Can say that it stays up in space a long time once it starts on its way up there. I think it just set the record of over 700 days, or forget the exact number. CST-100 Starliner, this is why we're here today. CST stands for Crew Space Transport, and the 100 is because of Boeing's been in operation for more than 100 years. And Starliner, of course, builds on the tone of being a commercial spacecraft, one that's opening up space to the world, to a bigger population than before. Next, we have the Space Launch System. That is the big rocket that is being put together down in Louisiana. We had core complete declared yesterday, core stage complete, that is. And it is heading to Stennis for the green run, which is a full duration firing of the engines. And then it's going to go to Kennedy Space Center and be the first SLS launched in 2020 or 2021. And then Phantom Express, which is a conceptual booster that can fly back after sending its payload into orbit. This one, the idea is to have a launch vehicle that can launch 10 times in 10 days. We've already done engine testing that proves that we can do that, and so that program is also moving along. Starliner's operations stretch across the country and involve more than 400 suppliers in 38 states. In Florida is where the program is based. That's where we have the Starliner factory, and it's where the launch site is. It launches from Cape Canaveral at SLC 41, Space Launch Complex 41. They assemble it there, do the final processing, and it's the launch control. All that is typical with NASA's human space flight, and wherever we could, because that system being as proven as it is, we grafted onto that. Here in Houston at Johnson Space Center, we do astronaut training for Starliner, and we also will do flight operations from Mission Control. Starliner Mission Control will be in the white flight control room right down the hall from the ISS flight control room. And in fact, a number of our flight directors are shuttle veterans, and they're all space station veterans. So it's a good group of specialists. Really excited to work with them, get to see them a lot during rehearsals and things like that. And I think it's going to be a spectacular mission coming up. Our landing sites are White Sands, New Mexico, and Dugway, Utah, Wilcox Playa in Arizona, and Edwards Air Force Base in California. White Sands is the preferred landing site, but if the weather's not good there, that's why we have the other options. You might notice that all these are in the southwest United States, and they are all desert areas. And that's because for Starliner, we're coming back to land on land. So we're going to be the first American capsule to land on land, under parachutes, on airbags. The idea is that by landing on land, you're not immersing the spacecraft in salt water, and you can use it again. The Starliners are designed to be reused 10 times. This is what the orbital flight test mission is going to look like. Again, we do not have any crew on board, but we are flying the profile and with all the conditions as if there were astronauts inside, because we're going to fly this exact same profile with crew on the crewed flight test. So step one, of course, starts in Florida. We lift off from Cape Canaveral Air Force Station. 12 minutes to 17,500 miles an hour in an orbit below the space station so that we can catch up with it. Our launch window is instantaneous, and that is, what that means is when the launch site at Cape Canaveral is in the plane of the International Space Station orbit, we have to go right then. So if the weather's not good at that moment, we can't just wait 10 minutes for it to get better. So we're aiming right for that specific window. We get up into orbit, and as soon as, again, just like with shuttle, just like with Apollo, with the previous programs, as soon as the bolts blow and the rocket starts moving on the launch pad, control of the mission switches from Florida to Houston. So on the OFT mission, there is one difference mainly with the crewed flight test, and for this uncrewed flight test, we're going to do a 24-hour rendezvous and docking. That is because since the spacecraft is flying by itself for the first time, we want to do a number of demonstrations, and allowing the time for those demonstrations and for the mission management team to make sure the spacecraft knows where it's going, knows where it is, and is behaving as it's supposed to. That's why we're taking the extra time. So 24-hour rendezvous for orbital flight test. For crewed flight test, with the astronauts on board, we're going to do our regular flight profile, which is a 6-hour rendezvous. As we close in on the station, we're going to take a number of opportunities to do a series of burns that'll steadily raise the orbit of Starliner. And during these, Starliner is going to adjust from kind of a GPS navigation system to one called Vesta, which actually sees the space station the same way people see. It's a vision-based sensor system. And what I mean is it looks at the station, kind of knows how it wants to look at different times, and it flies itself to get into a position in front of the station and then in line with it and then steering itself in. So if you think of when you're setting out on a long trip to somewhere, maybe you don't know exactly, but say you want to drive from here to a Holiday Inn in Dallas. You set your Maps app, you head off, and then when you get closer and you have to pick the parking place, you're not relying on GPS anymore, you're relying on your eyes, and you're steering right into the driveway or right into the parking spot. We're going to spend about 7 days docked at the International Space Station. And then we're going to undock on the 28th in the middle of the night or early morning, and then start to fly back to Earth. So flying by itself, it's going to fly around the space station, get some imagery there. Its sensors will record exactly what the space station looks like from all angles. Then it'll back away and behind the space station, fire its thrusters to slow down from that orbital velocity. Just a couple hundred miles an hour makes a big difference. Then we're going to jettison the service module. That's not going to be reused. That's going to burn up in the atmosphere. And the service module just has the consumables. And then Starliner itself is going to make the plunge down toward New Mexico. It'll come down on parachutes, and then just before touching down, it'll drop the base heat shield, and a series of airbags will inflate. When we did this for the pad abort test, it landed so softly, even with 2 parachutes, it landed so softly that it did not deflate the inner airbags. Each airbag has an outer airbag and an inner airbag, and it did not land hard enough, even under 2 instead of 3, to deflate that second inner airbag. So it'll sit there in New Mexico just for a little bit while our ground convoy comes out and recovers it. Starliner is, of course, composed of a number of parts. Ascent cover on the very top, that goes right into the water about 4 minutes after launch. When the first stage of the Atlas V burns out and separates, the ascent cover also separates. That protects the Vesta system and its sensors on the ride into through the thick atmosphere. Next, we have the forward heat shield. That stays intact until we're coming back to Earth, and it covers the parachutes and protects them. Next, we have 3 parachutes and 3 main chutes. There's a number of drogues and pilot chutes along the way. And then we have the Starliner capsule itself. And that is the part that is reusable. So that's the part that has the avionics, the life support system, all the things that make a human spacecraft capable of protecting astronauts. It's the most sophisticated part of the whole stack, so that's why we opted to reuse that part of it. Next, we have the landing airbags. Again, those are to provide that last bit of cushioning when you're landing on land. They also deploy if they have to land in the water. And we're not nominally supposed to do that, but we are positioned to do that in an emergency because Starliner has a launch abort system. So if something goes wrong with the rocket on the way up, it can basically act as an ejection seat of sorts, but with the whole capsule. Pushes away from the rocket and can land in the water. Next, we have the base heat shield. This is the part that takes the brunt of the 3,000-degree reentry. When the plasma is forming around the spacecraft, that base heat shield, it's an ablative heat shield, very similar to the ones, much lighter weight than the ones for Apollo, but using the same ablative principles. And that gets dropped right before touchdown and it is not reused. Next, we have the service module. Again, consumables for much of the mission, and it also holds the thrusters that are used to steer the spacecraft in orbit. The reusable crew module also has a small series of thrusters, but they're really to maneuver for only a few minutes and really position it for the return to Earth. Service module has the robust ones. We call them the OMACs, the Orbital Maneuvering and Control System thrusters. Each one of those produces 1,500 pounds. So when they fire, it's a 6,000-pound kick to get it into orbit and then to raise its orbit in the early parts of the mission and then to slow down when it's coming back. The RCS, the Reaction Control System thrusters, those are for fine adjustments. Simple pointing of the vehicle, a little bit of speeding up, a little bit of coming back. Those are essential, of course, for the phases of docking. Then the launch abort engines, those are each 60,000-pound thrusters. 40,000-pound thrusters. They burn hypergolic, which is a hydrazine and nitrogen tetroxide combination that ignites and lifts the spacecraft away in case of danger. And the last part is the set of solar arrays that are on the back of Starliner. Starliner's batteries are charged just like the space stations, which is by converting sunlight into electricity. So most of the time when we're in space, flying on our own, we'll be pointed with those solar arrays toward the sun. So it's called tail sun. And while it's orbiting, positioned that way, and even while it's at space station, docked on the forward port, it's positioned to charge the batteries using those arrays. And we also have the Atlas V stack, United Launch Alliance booster, 191 feet tall. This is the Atlas V, and it is related to the Atlas I that carried John Glenn into orbit. It's related really in name. The Atlas I was less than 100 feet tall. This one's 191 feet tall, and of course the thrust of John Glenn's vehicle was less than 1 million pounds. At liftoff, this one has about 1.7 million pounds. So looking from the top where you have the Starliner spacecraft, next comes an aeroskirt. That gets jettisoned right before Starliner gets into orbit. The aeroskirt basically smooths the airflow coming over the rocket as it goes through the atmosphere. You have the adapter, of course, that connects the Centaur upper stage to the Starliner. Big steel part. They've milled a few of them, and they are about as well. They're very strong. They're also very heavy, but that's another thing. Then you have the Centaur. The difference with the Starliner Centaur is that there are two engines, and that's both for redundancy and for power on the way up. Most Centaur engines, all the ones that have flown before, have been single engines, the ones that have sent the planetary probes and all sorts of satellites into orbit. Powered by RL-10 engines. Both of the engines for the Centaurs have, of course, been tested down at Aerojet Rocketdyne's facility in West Palm. Next, we have the stage adapter connecting the booster stage to the Centaur. And then we get to the booster stage itself, powered by an RD-180 engine that produces around 900,000 pounds of thrust. Liquid fueled, it burns kerosene and liquid oxygen. The solid fueled boosters, we'll use 2 of them. Atlas V can use up to 5 depending on the spacecraft and its destination, but for Starliner, we're going to go with 2. And then you have the thrust structure itself and the RD-180 engine. And the big difference between Starliner and any other payload that Atlas V has carried is, of course, the human element. Starliner was envisioned right from the start, of course, to be an astronaut's vehicle. This is Chris Ferguson. He's the commander of the first Starliner crewed flight test. He will be in launch control and mission control during the orbital flight test coming up. And he has been instrumental in the development of this vehicle. He is, as near as I can tell, although astronauts have, of course, had a lot of input in previous spacecraft, Chris has served as an executive in crew flight development of operations and the vehicle itself. At the same time, he is training for the mission. So this vehicle carries a lot of his fingerprints and a lot of his dedication. He's great to work with. If you ever get a chance to meet him, I think you'll be as impressed as anybody can be. You can see that Boeing also has a spacesuit, a Starliner spacesuit of our own. We worked with David Clark on this one. It's designed to be used inside Starliner. It's not one for going outside and making spacewalks with. It's light, and the visor is connected. It kind of, if you think of it as an ambitious hoodie, that's really what it is. And the reason for that is that Chris, when he was a space shuttle commander, he's a veteran NASA astronaut who retired from NASA, and when he was flying shuttle, he was, he's sitting there in the commander's seat, and he's coming back, and he's been in weightlessness for 2 weeks. All of a sudden, there's gravity, and you have that thick metal ring that holds the helmet to the rest of the pumpkin suit there. And as soon as you come back and that gravity starts to hit, that ring starts to push down on your shoulders. And he said by the time he got finished flying and landing, his shoulders hurt more than if he had just been sitting all morning in the gym working his shoulders. So the first thing he asked was that there not be a neck ring. So that's why we ended up with a zipper, and we can pull it over. It's a plexiglass, and then zip it closed, holds the pressure, and they're in good shape. You can see in this video that he's training to put it on while inside the vehicle. The Boeing mission trainer that's over in Building 9 is where this was done, where both of these were filmed. It looks tight in there. It holds up to 7 people. And the first thing anybody says when they look in is, wow, it looks cramped. And it does, but I'm 6'1", and I can move around in there. I couldn't the first time I got in, but that's why they do it, so they can learn how to move around in there. It's about the same interior size as a mid-size SUV. The good news is 6 hours here, and then you get to move into the space station, which has the same space as a empty 747 or a 6-bedroom house. So they learn to move around, they learn to get in their places. You'll see that the control panel, the little box right there, much smaller. It covers basically 1.5 or 2 seats. In Apollo, that went right across all the way, and in Shuttle, they were all surrounded by switches. There are 67 switches in Starliner. Mostly that's because the avionics let it fly itself. It has 2 big displays. They are not touch screens. Instead, they have edge buttons. The reason for that was that when we tried touch screens in a centrifuge, and you get into the launch forces, the vibration, the G loads, going up and coming back, you don't really know what a touchscreen is going to do. And if you think about trying to dial your cell phone while you're driving fast down a gravel road, that's kind of what it's like. You might think you're hitting the 8, and you end up hitting the 5. Who knows? That's not something that you want to be in a condition of when you're doing the important stuff of flying up and flying back. So we went with edge buttons. And the switches are all for the primary elements. So if they have to take control of the vehicle, then they want to deploy the parachutes, they flip a switch, they push a button, they know that the computer's been told to deploy the parachutes. Also, the flight control system operates manually even if the computers aren't working through direct links. Very important to have that backup, full control of the spacecraft. A lot of integrated testing has gotten us to this point. Parachute tests, drop tests, service module hot fire, a lot of structural testing. By the time this vehicle goes into space, we have a whole envelope that we know how everything works and how it works together. With pad abort tests, that was the first time that we had been able to integrate the crew module and service module through a dynamic phase of flight. Came out great. We had the third parachute issue, but I mean, I was there, I saw everything take place. It came down stable as a table on 2, landed very softly. You build in that kind of redundancy. It was a set of data they didn't expect to get, but they were very pleased with.
8, 7, 6, 5, 4, 3, 2, 1, 0.
Liftoff.
Roll complete. LA cut off. On track. Comet cut off. Get your on. 40 kill parachute. Broke parachutes mains. SM7.
It's a very proud moment for me. Should be a very proud moment for the entire Boeing team who've made this happen. And hopefully our NASA customers are equally happy with the progress that we've made. And it's a great day for the United States of America.
2 mains fully disreefed. Base heat shield jettison. Airbags inflating. CM touchdown.
So we were really pleased with the way that went. Next up, we have the flight profile of Starliner. This is the way it's going to look as it's climbing into space. Again, flight profile will go from 0 to 17,500 miles an hour in 12 minutes. Never crossing a higher G threshold than 3.5, which is basically the same as they encountered during shuttle. The perforated area right there, that was something that they added in midway through the design, and that's really where you see the stable flight. That's why on the pad abort test where it was going up and even after some of the deployment actions, everything was very stable. You didn't see a lot of tumbling. There's a lot of forces, of course, on a spacecraft as it's heading up into space, and anything that we can do to smooth that out really seems to pay dividends. That's the ascent cover jettison. You'll see the aeroskirt go. In this one, although there's not a crew on board, one of the items that we have sitting in the commander's seat is an anthropomorphic test device. It's a fancy way of saying crash test dummy, but we don't want to be that rude about it. She is Rosie the Rocketeer. homage, of course, to Rosie the Riveter from World War II, and really a tribute to all the women in aerospace and to all the men and women who have made Starliner get to this point, who have been working very, very hard to advance the program. She will be in a Starliner spacesuit and outfitted with a lot of different sensors, and by the time she comes back, we're going to know exactly what astronauts will encounter during their flight. Goes up to the space station. Little adjustments here and there. We don't really expect it to be that many firings on its way to the space station, but it's ready for it. And then extending the soft capture ring, aiming for the international docking adapter that is on the forward port. Then it closes in, and the moment that it touches, that's considered the successful docking point. It has reached space station and connected. The soft capture ring retracts, takes about 4 minutes or so, and then a set of hooks engages. Next, when we leave, this is Starliner flying around the space station. And really, we took that direction so that the sensors can get a picture of the space station with the Earth behind it, because Earth, of course, reflects a lot of light. The cloud tops and everything reflects a lot of light. So we want to be able to show Starliner's sensors what it's supposed to look like, because one of the other docking areas for Starliner will be on the space-facing side of the space station. So it's going to have to guide itself even while it's looking at that bright reflection coming off of Earth. Coming back, saw the service module jettison, plunged through the atmosphere, 3,000 degrees Fahrenheit at entry interface. Then falling through the atmosphere, this is the part where all of our hearts are in our throats. I think we'll be able to have imagery from one of the NASA chase planes at this point. And you see the series of drogue chutes and parachutes to pull the forward heat shield off and then open the parachutes themselves. The bucket handle, it's officially called a rotation handle, but it just kind of makes it look like a picnic basket. But that's to level it off. Because we're landing on land, we need it to be level when it touches down. So that's why the bucket handle. Comes down and gentle touchdown. And we all breathe for the first time in a week. This is a little bit more spelled out profile of the ride up, RD-180 at ignition and the 2 solid rocket boosters. Then that gets jettisoned about 4.5 minutes in. Centaur takes over, the dual engine Centaur, pushes Starliner up and then a little bit parallel before picking up again. And the whole reason for that is because Atlas V is nominally set, when it's not launching a human spacecraft, it's set to launch satellites into orbit, of course, and it has a higher angle on its way into space. But because this is for a human vehicle that needs to be able to abort a launch if something goes wrong, the rocket has to fly a little bit of a different plan so that it keeps the spacecraft in a position to abort the launch. Once it's in orbit, 31 minutes in, we'll do the orbital insertion maneuver. That's a 40-second firing, and that just circularizes Starliner's orbit around Earth. This whole time, it will be in the 51.6-degree plane of the International Space Station. And in order to fly that precise path, it will be a little bit below station, makes its orbits, does a few demonstration burns, and then begins other height adjust burns where it lifts Starliner's orbit, getting slower in relation to the space station each time. Do a number of maneuvers. They have acronyms like NHPC, and SRPC. Please don't ask me what those are. They're mainly holdovers from Apollo. I've asked the flight directors, and they were stumped too, so I feel pretty good about that. They had to name them something, is what I was told. Then we close in, and we dock with Space Station. This is what it'll look from the outside. This is the Vesta system that I was telling you about. This is the different ways that the spacecraft will see Space Station as it closes in. It's looking at the shape of station and determining from that shape exactly where it is, where the spacecraft is in relation to the station, whether it's flying beside it, below it, above it, and it'll use that and use its thrusters and steer itself in. For undocking, basically the reverse. The difference is the fly around. After Starliner backs away from the station, gets outside the keep out sphere, which is an imaginary area where only vehicles that are going to dock with Space Station or rendezvous with Space Station are allowed to go in. After it gets out of the keep out sphere, it will then proceed over and above the station, then down and below, and then one more time halfway around to get behind the station, and then outside of the approach ellipsoid, and then Space Station does not have to worry again. Meanwhile, Starliner will just be beginning its ride back into back to Earth. Here's a little more detail of the landing cycle. Forward heat shield jettison, drogue deploy, pilot and main chute. The pilots come out, they basically pull the main chutes out afterward. Rotation handle opens, base heat shield, airbags, land in the desert, happy ending, everybody's happy. And this is where we are today. This was during our wet dress rehearsal last Friday. You can see the Atlas V venting. And in the middle is when we first rolled out. That was our first rollout last week. Throughout all of this, even though there's not a crew on board, we are always mindful of Chris Ferguson and NASA astronauts Nicole Mann and Mike Fink, who will all be flying on the crewed flight test coming up. And there you see the white room and how Starliner looks from the white room. That's the hatch. The crews will get in. For our use, the ground support team will be loading last-minute items into the vehicle through that hatch. And of course, reminiscent of what we saw during the shuttle days. Chris Ferguson, Mike Fink, Nicole Mann. I suspect you've all met them more than a few times around here. Great folks to work with, very exciting. And the space station, our destination, and a spacecraft that is really unlike all others. It's been up in space since 1998, so it's 21 years old. And of course, we're in the habitation. We're in our 20th year of habitation. Officially, the 20-year mark will come up November 2nd of 2020. We're marking it as a whole year of accomplishment. By we, I mean Boeing and NASA, of course. And 20 years of fantastic research, test bed, technology, a proven area, and it's hosted astronauts continuously since 2000. Another look at some of the life aboard station. It's something that's been such a constant presence that sometimes take it for granted. I know we don't here in Houston, but in other parts. See the spacewalks that they're doing, and of course the view from Earth, which is unparalleled. See some of the crew members working there in the cupola. And a lot of scientific capability. One of the things that I like most about Space Station is that it democratizes research. What I mean is research is that opportunity to do space research. The Space Station has opened it up to a lot of people. There are students through Genes in Space and other programs who fly their experiments in space. Never would have thought that would never would thought that would have happened. Always hoped it would, but space station has really made that possible. The work on space station, half of it for the American side, half of it is run through the ISS National Lab for a lot of different scientific areas, but the other half, and what NASA's really been focused on, is proving technology for deep space. And that's something that we're also working with, of course, at Boeing. And you can see some of the influence on our gateway design and gateway logistics and lander. And ultimately, of course, a lunar lander. So I think you can see really the influence in technology and design, taking those lessons that are learned from the International Space Station and applying them, making it more reliable, making the deep space program more reliable and ready to move on. My opinion is that because of the success of space station, where water is recycled, air is recycled, and the life support systems work for years and years at a time. And I think that really makes this drive to deep space feel more real, certainly more possible from a technological standpoint. Y'all have probably heard of the other deep space steps that have been made before space station. And they rarely get out much beyond the starting blocks, but we're pointed toward the moon and to Mars. And I think space station, when we look back at this, the path to success, the difference is going to be that we've had all these years of space station and to prove all those technologies, to try out these inventions.